Hey everyone, today we present to you our research on a new DNS vulnerability class in DNS-as-a-Service providers. My name is Shir, and I lead the research team at Wiz, the cloud security company. With me on the stage is Ami, the CTO of Wiz.
Thank you. It's really great to be here. Just a bit background on the team. So we are the Wiz research team, highly experienced team of researchers, many of us with background from Microsoft Cloud Security. And the goal of the team is to do groundbreaking cloud research and find vulnerabilities and risks and attack paths that are unknown today that may affect cloud environments. So how do we get to a research on DNS? Let's start from the beginning. Why DNS as a service? So in fact, DNS as a service is one of the most important and critical services that cloud providers give today to customers. And why is that? DNS, first of all, is the lifeblood of the internet, but not only for the internet. The internal DNS is the service that powers all of the routing between endpoints, between internal services within the company. So DNS is a critical service that companies use, and now companies are transitioning to use DNS as a service. Now, it's not only that it's really impactful. If I would be able to do something with DNS, the impact could be huge because it affects not only the cloud resources the company has, it also affects the on-premise resources the company has. First of all, the domain, the company domain is a company asset, and the endpoints of the company are using DNS as well. So if you think about it, the effect of this cloud service goes well above and beyond the actual resources that the company has in the cloud. And third, and maybe most important for researchers, is that DNS is highly complex. It's a very ancient protocol. It's with us since the 1980s. It has so many different implementations, not only by the providers, but also there's so many different DNS clients. And these DNS clients can implement the DNS and algorithm in different ways. More than that, DNS is not only routing on the internet. There's so many different protocols and algorithms used for dynamic DNS and for authentication over DNS. And those algorithms, many of them were developed 10 or 20 or even 30 years ago. So this gives amazing attack surface for us to explore. So we started looking into DNS as a service. And as cloud researchers, obviously we started from Route 53, which is probably one of the most popular DNS services provided by cloud providers. And initially, we looked at misconfigurations that users can do within the platform. For example, if a user registers a domain to a cloud object like a load balancer, and the load balancer doesn't exist anymore. So these kind of misconfigurations. But as we started learning more and more about Route 53, we thought maybe we can actually find vulnerabilities in the way that the service actually provides DNS to customers. And that's how we started the research into the vulnerabilities in Route 53.
So at the beginning, we thought about domain hijacking. Domain hijacking sounds scary. If a malicious actor managed to hijack a domain, the effect can be massive, and we thought it might be possible. So Amazon has around 2,000 shared DNS servers, serving thousands of customers. This is basically the idea of DNS as a service, sharing DNS servers with multiple customers, so many customers are managing their domains within the same server. Whenever a customer is registering a domain on the platform, they get 4 shared name servers. These are the servers that now manage the DNS zone of that domain. Our initial target was hijacking our own domain, wiz.io. Before going into details, first brief overview of how DNS works. Each domain must have a DNS server called name server that will store its records. Many companies manage their name servers themselves, and many other companies use existing services like DNS-as-Service providers. In our case, at Wiz, our domain is hosted on Amazon Route 53 and is managed on 4 name servers you see in the right of the slide. When a customer wants to connect to a Wiz server, they query one of these servers for the with.io domain. So far, so good. The thing about Route 53 is that all customers are using the same name servers, and each client can manage their domain on any server on the platform. We can see in the slide that the Amazon name server, the NS1334, which managed with domains, it also contains domains of other customers, as you see in the right column. And here we had an idea. What would happen if we will manage to add duplicate entry of with.io into the same server? This should be impossible, but if we succeed, might cause a conflict with insane outcomes. So we tried to host the Withio on Route 53. And to our surprise, it is possible. Anyone can register which domain they want on the platform. There is no restriction on whether the domain is already registered, and there is no ownership verification. But as you can see in the slide, we got 4 name servers other than those, other than the original with name server. And we tried to add it again, and again, and again, and each time we got a different name server. But we never got the same servers to which the original Withio points. We tried to register subdomains of Withio and even pad the domain with special characters, all without success. So after we failed to hijack the domain, we tried to think about the problem from a new angle. Which domain can we possibly register in the platform that, 1, it does not exist in the name servers, because if it is, we will not be able to register it on the same name servers, and 2, DNS client must query for it, because if the domain is not queried, it has no effect. So we thought about it, and then we came up with an idea. What would happen if we register one of the official AWS name servers on the platform? What would happen if we register one of the Route 53 name servers under the same name server? So we choose an arbitrary name server. In this case is the Route 53 name server NS852. And we try to register it on the platform enough times that at least once it would fall under the management of the same name server. Let's do an illustration. Here you can see an illustration of how the NS852 name server, an official Route 53 name server, looks like. You can see it contains DNS zones for several of Route 53 customers. What do you think would happen if we manage to register the name server domain name, the NS852, under its own management? I truly don't know what would happen, but we must check it out. So we tried it, and it worked. As you can see in the slide, our new domain is now managed within a name server with the same domain name. We were really excited. We didn't know if it will have any impact, but we had a good feeling about this one. To test the effect of what we did, we decided to specify an A record pointing to our server. So now, if anyone is trying to talk to us, we would be able to listen. We ran TCP dump on our server and hope to see something interesting. Surprisingly, we started receiving thousands of requests from thousands of different IPs. We realized we were onto something. The next step in the research was to analyze all these DNS queries and figure out why are they coming to us.
But wait, why are we getting any traffic? I mean, think about it. Just like we did with Withio, if you register a domain on the wrong name server, you're not supposed to get any traffic. We registered the name server on itself. We didn't expect to get any traffic. What's going on? So what we did initially is just initial analysis, trying to understand what kind of DNS requests we're seeing. And that became even more weird, because this was not just general DNS traffic. We were seeing dynamic DNS. Dynamic DNS is traffic that you wouldn't expect to see at all in external networks. We were seeing IP addresses, computer names, domain names. So let's see how this looks like. So this is an example of a packet, one of millions of packets we were seeing. So we were seeing the external IP of a computer, and an internal IP of a computer, and a computer name. It really quickly became apparent that we were seeing millions of endpoints coming from different organizations. We had no clue at that point, why are we seeing that? What does it mean? But there was clearly something big here going on, and we definitely wanted to understand what's behind this. So we actually dug deeper. What we did is we registered not only one name server, we registered all 2,000 name servers in AWS and tried to figure out what are we actually seeing. And we started tapping into a portion of the worldwide DNS traffic going to organizations. We were seeing more than 1 million endpoints coming from more than 15,000 organizations, all of them using a Route 53 as their DNS service. So it's huge amounts of data coming from millions of endpoints. But what's going on? And when we dug deeper, we saw that it's coming from big companies, Fortune 500 companies, more than 100 government agencies. So this is not just a limited feed we're getting. This is also high value targets that we're seeing. So we really need to figure out what's going on. So let's just summarize what we know so far. We registered a domain name server to itself. We didn't expect anything to happen, but what did happen is that we got millions of endpoints sending dynamic DNS traffic queries to us. So what's going on? The next step is to dive deeper into the world of dynamic DNS.
So what exactly is dynamic DNS? Dynamic DNS is a DNS extension specified in RFC 2136, and it allows clients to dynamically update DNS records of target DNS server. It is commonly used to help devices find each other in internal Windows networks. Let's see how it works. When my Windows computer joins the company's network and receives a new IP address, it updates the local DNS server, which is called master server, on its new IP address. Now, when Ami is trying to connect to my computer, he can query the local DNS server about Shir PC. And the master server will answer with my current IP address. So far, so good. But wait, why endpoints send DNS updates to our server? These are requests that should never leave the internal network. Could it be that the endpoints think of our server as their master server? How do they even know how to find their master server? So it turns out that Microsoft has its own algorithm for finding the master server. It does not work exactly as specified in the RFC. So let's dive into the algorithm. When a Windows endpoint wants to update the internal master server for its new IP address, it first needs to find it. The endpoint will send a SOA query to the internal DNS resolver on its own domain name. The internal DNS resolver knows that the Withio DNS zone is managed internally. So when queried, it will return the internal master server within the SOA response. So as you can see in the example, on the slide, the DNS resolver returned the internal DNS within the network. Now, when the endpoint found the master server, it will update it, as we saw in the previous illustration. And the update succeeded. So far, so good. But what happens if the corporate DNS resolver is not set correctly and does not contain a DNS zone for the local domain? Or what would happen if the computer is configured to work with external DNS resolver, which is unfamiliar with the internal resources inside the network? What happens when the computer leaves the organization and starts working from external DNS resolvers provided by home routers? In that cases, when a computer queries for the corporate domain, the DNS resolver will treat it as an external domain and return the master server of the external domain just as it will do with any other domain name, which is where the problem starts. So imagine an employee of Withio decided to work from home, like most of us lately, and connected to their home Wi-Fi. The computer got an internal IP address from the home router and now trying to find the local master server. Because the external DNS resolver are not familiar with Withio, it's going to resolve it just like any other domain. Because the domain is managed on Route 53, it will return the Withio master server as specified in Route 53. This is the primary server. This is the master server that was specified in the SOA record within Route 53, and this is the default record. The endpoint will then try to update the master server, which is an Amazon shared server that manages thousands of customers. Obviously, Amazon server does not support dynamic DNS, so the update request will fail. Microsoft algorithm does not give up here and believes it's still having a chance to find the master server. The next step will be to check if Withio name servers have records of that's the same master server. So the DNS client connects directly to the IP address of the name servers and asks them, what is the IP address of the master server? In our case, it is the same domain as the name server. And here happens the interesting part. In fact, Windows DNS client queries the name server for itself. And if you remember, we have registered this DNS zone. And here we can return any records we want. So we returned our IP to the DNS client, as you can see in the slide. And now the computer will update our server with DNS updates. This is crazy.
So what did we learn so far? So now we can start understanding why we are getting so much traffic. Windows endpoints have a custom algorithm in order to actually implement dynamic DNS to find the master DNS server. And this algorithm, as part of the algorithm, actually queries at some point the name server for its own name. Again, this algorithm is geared towards internal networks, but when used on external DNS providers, then unexpected results occur. And the unexpected result is that when we put our malicious DNS server, it was actually getting traffic from the dynamic DNS traffic from millions of endpoints. And so now we can start understanding the initial question of why are we getting so much traffic? So now the next question is this traffic really interesting? What do we have in these millions of devices actually sending traffic to us? So as we started analyzing the traffic, it soon became apparent. What we've created in a simple domain registration is a nation-state intelligence capability. We were able to actually map thousands and dozens of thousands of organizations across millions of endpoints. Let's think about it. If I have an organization, I can map the external IPs. What does that mean? I can map office locations, home locations of the entire organization. Multiply that on tens of thousands of organizations. I can see internal IPs. That means I can start building internal IP ranges. I can see computer names. That means that I can understand what the organization is doing. I can understand and map their internet network. This is a full intelligence map on my hands for thousands of companies and even government agencies. Let's see how it looks like. So let's start from what we call IBBased Intelligence. We can map a company, and this is, by the way, one of the top services companies in the world. We can map the entire company. Here you see more than 40,000 endpoints that are actually spread around the world. We can see all of their office branches. We can see their home locations, all of their employees. We can actually map them. Now imagine that for government agencies, for different companies, right? I can even zoom in on specific office locations. Here from this office, we saw 600 endpoints reporting to us. So we have amazing intelligence on thousands of companies, but it doesn't stop there because we also have the ability to leverage those kind of intelligence to actually ask interesting questions like, and these are just a few examples that we found, there is the Foreign Assets Control regulation that says that some companies are not supposed to work from some countries. So that would be interesting to find, for example, that a specific Western mining company has offices in the Ivory Coast, which is forbidden. And again, we see that simply from the data. Or another interesting example, a credit company has a subsidiary in Iran. And we can see that there's a few locations here, 13 endpoints we detected in Iran. So just to understand the extent of this data, this is really an intelligence capability. We can see we're tapping into DNS traffic from so many organizations that it's giving us a lot of visibility into what's going on. Now, this was external. Let's go deeper. We are actually seeing IP ranges. We were able to map different IP ranges and the actual network mapping of those organizations. We can see, for example, this is the employee network, this is the CI/CD network, this is the operational network. Now, how do we know that? Because we see the computer's IPs, we see their names, so if you combine them, you can start understanding the actual role of each IP range in the company. So we are mapping externally those organizations, and we are starting to build internal mapping. But it doesn't stop there. We're also looking at computer names. So the computer names also reveal information about the organizations. Like, this is a machine running Windows. I can see a build. This machine is from finance, right? So computer names help us build the intelligence map on the organizations that we're looking at. So we have thousands of companies. We have the ability to map them externally and internally. Is that all? So it appears that we can even continue. We saw a lot of traffic coming up from IPv6. And that intrigued us. There is a known argument around the world about the security of IPv6. IPv6 doesn't use NAT. So there is a possibility, if I see a IPv6 address, to actually access the device directly. So we tried it out. We actually saw that 6% of the IPv6 addresses that we were seeing, and remember, these are endpoints of companies, these are organizational endpoints. 6% of them, and maybe 6% doesn't sound like a lot, but 6% is actually thousands of companies that we are seeing endpoints that we can actually directly access from the internet and have open protocols like SMB, RDP. This is crazy. This is like actually allowing us to even start an attack using those addresses. So I know that there is a big debate about IPv6, but what we are seeing here is very interesting data. If I have a way, like we have here, to tap into IPv6 addresses, the argument that says an attacker would never be able to scan the IPv6 address range, this argument fails, because using an example like tapping into DNS allows us to see millions of IPs and basically potentially start attacking those devices. So just to understand what we've seen here, we are able to build a very powerful capability. Now the scope is much, much bigger than we initially thought. We started from Route 53, but then we continued on the research. And we saw that additional service providers are susceptible to this vulnerability. And we believe that many, many more are vulnerable. We are currently in disclosure process with several of them. But this means the scope here can be much more than just DNS-as-a-Service providers. It can be domain registrars. It can be shared hosting. Basically, anyone that's providing DNS services might be susceptible to this attack. And all could be vulnerable to this kind of name server hijacking. So think about it. If we would have extended the attack, what would be the scope and the number of endpoints that we could put into our new intelligence capability? So in terms of the timeline and disclosure, we worked with Amazon AWS, and they acted really quickly. Once we reported the vulnerability, it was fixed. So it was fixed by February this year. And there's 2 more cloud providers that are currently in a disclosure process. Now, how did they fix the vulnerability? So it's honestly pretty simple. All they have to do is basically block the ability to register the name servers. And again, you would even think, why would they even ever allow us to register the name servers? Obviously, we don't own the name servers of AWS. And maybe that would be part of the resolutions that could be for this kind of attacks. So basically what AWS did is that you cannot register anymore the name servers, and that blocked this specific type of attack. We also disclose this to other cloud providers that are currently working on a fix, and we also disclose this to Microsoft. Now, what's important to say here is that Microsoft told us that this is not a vulnerability, and they're right. This is actually not a vulnerability. The problem here is that the DNS of the company is misconfigured. The misconfiguration here is that the public DNS didn't expect the endpoints to actually think this public DNS is their internal DNS. The problem here is actually what I call sometimes international waters. It's not exactly a vulnerability, but still it has a huge impact. So basically, this misconfiguration happens in so many organizations that the impact is huge. But we can fix that. So let's now talk a bit about how this vulnerability can be fixed.
So DNS providers want to ensure that they are not vulnerable, should make sure it is impossible to register their own domains on the platform. DNS providers who want to have even a better security can also do ownership verification to ensure users are only registering their own domains. In addition, it is important to make sure that the platform user cannot register a reserved name, as specified in the DNS RFCs. The RFC is full of reserved domains that should not be allowed to register, and their registration may lead to unexpected behavior. For organizations that want to make sure they are not vulnerable, we recommend making sure that the primary named server in their SOA record in the external DNS does not point to a default domain owned by the DNS provider. As you can see in the slide, the default primary name server that the domain owner receives when they add their domains to Route 53 is the first name of the four name servers which manage the DNS zone. Changing it to the organization primary name server, or even to an invalid subdomain under the domain, will solve the problem and will not allow potential attackers to register the domain on the platform. We are getting to the end of the presentation, and I want to recommend some research directions for researchers who may want to continue our research. During the study, we found more interesting domains that can be registered on DNS-as-a-Service platforms. Any domains that is considered reserved by the RFC is interesting. We had some playing with reverse DNS reserved names, like the .arpa family, and we managed to get connections from a variety of endpoints. Another research direction we have is to scan DNS servers in the world and try to update them with Dynamic DNS. Sure, there are servers that do not verify authentication, and it will be interesting to understand how many of them are there. Another research direction that we find interesting is the NTLM authentication in DNS updates. Perhaps it's possible to take advantage of the fact that the computer in an organization is trying to authenticate with us. It might allow some NTLM attacks that could grant an attacker an easy entry point into the exposed organization. So apparently, Dynamic DNS enabled authentication, which sounds very reasonable. Letting anyone in the organization to update any DNS records they want sounds a bit risky. Windows computers perform authentication using NTLM or Kerberos over DNS TSIG. To force endpoint to authenticate to us, all we have to do is to respond with a refuse message to their update request. The computer will then attempt to authenticate. Not every computer has done authentication with us, and we do not know in what it depends. Here you can see an authentication request we received from a Windows 10 computer using NTLM. The fact that it is possible to get a computer to do an NTLM negotiation with us sounds really cool, and it may be possible to leverage it. We have not continued this research direction. So, what have we seen? Just a quick summary and key takeaways. We got to nation-state capabilities after doing a simple domain registration. So, and this scope is not only for a specific service. We saw that the scope may be much bigger. So there is a huge scope here, but it's not only, we believe it's not only the domain name of the name server,
we believe there may be many additional domains that you might register that might break things. Because as we saw here, you can never expect what DNS clients will do. So we see this as a new class of DNS vulnerabilities that are trying to leverage the fact that DNS as a service works a bit differently than DNS providers that we had on premise. And using that fact, try to find completely new attack vectors that are completely uncharted and maybe untraceable for companies. So thank you for taking the time. We hope that the security community will start looking more into DNS-as-a-Service vulnerabilities. We would love to cooperate and work with anyone that would want to help us in further research.